Morning, everyone. This is the third and last day of our 3-series workshop. The first and second day, we went over the services that we provided. We introduced some brief list of statistics that we conduct in our center. Today, we'll do some practice with you and show you how to do a certain analysis using SPSS software. So we'll go over this, we'll discuss sample data and goals of the session. We'll have a little overview of SPSS with demonstration, and we'll also walk you through how to interpret results. And at the end, there'll be a Q&A session. So without further delay, I will ask ID to begin.
All right, thank you so much, Professor Sumari. So as we stated before, this session is a practical session where we will introduce everyone to the workings of SPSS and how to run statistical tests on SPSS. On this slide, we have sample data that we'll be using to conduct our statistical tests. And as you can see, the table shows performance data for electric vehicles that we gathered. And we would like to use this data to predict how the performance of these cars affects their sales price in US dollars. So some of the indicators that we'll be using to predict the price are the acceleration, the top speed, the range, efficiency, and fast charge. And as you can see, most of these indicators have a unit of measurement, because when we conduct analysis, we always want to make sure that we are measuring it through some units of measure. So for instance, if we wanted to use weight in pounds to predict someone's body mass index, we won't just represent it by numbers, but we'll represent it by units of measurement. So I would like to reiterate some of our goals for this presentation. So firstly, we would like to derive summary statistics using SPSS. In our presentation yesterday, we gave our audience an overview of some of the descriptive statistics that we run on SPSS, like mean, median, mode, as measures of central tendency, and then standard deviation and variance as measurements for dispersion of data. Then we are going to run a multiple linear regression analysis, which is a predictive analysis that is used by most businesses to make predictions about their future. And the multiple linear regression analysis will also include an overview of regression. And then lastly, we'll interpret the results that are derived from conducting the analysis. So without further ado, I'll move it over to Rabina to touch more on regression.
Thank you, Eddie. So before moving SPSS demonstration, we would like to talk about regression. So regression is a statistical method which we use to predict the strength and character of independent and dependent variables. So we have two components in the regression. Independent variables, we denote it by X, and it plays the role in determining the value of an outcome. And dependent variable, we call it as an outcome variable, and it is denoted by Y. Next one, we have simple linear regression. In simple linear regression, we model one independent variable and one dependent variable, and we predict the relationship between them. Here we have taken an example of using a person's weight to predict the BMI. So here weight is an independent variable, and it is taken as a predictor, and BMI is a dependent variable. So with respect to change in weight, we predict the BMI. This is the regression equation that we are going to use, and here beta naught is the intercept that shows the value of Y when X is 0, and beta 1 is the beta coefficient that gives the value of Y, which either rises or falls with respect to change in value of independent variable, that is X. So according to our example, we can set up the equation as BMI can be calculated with this equation, and this epsilon is the error term. So now this is the graphical representation of simple linear regression. Here, beta naught is shows the start point of the regression line. So here x is 0, that's why y is also 0. So this is the point where the line starts. With respect to change in x, the value of x, the y changes. If the value of x increases, the value of y also increases. So we will have rise in the slope. And if the value of x decreases, then the value of y also decreases. So we will have fall in the slope. So this is just a simple graphical representation. Now let's move on to multiple linear regression. In this, we model a series of independent variables with a dependent variable. So we have taken an example as predicting the grade of a student with respect to the student's study hour, attendance, assignment, and delivery method. So we have 4 independent variables here and 1 dependent variable, that is grade. So we model the regression equation as in simple linear regression, but we only have multiple slope coefficient, beta coefficients, and multiple independent variables. So the process is same as the linear one. Now we have some of the terms that we use in regression. One of them is R squared. So it is a goodness of fit measure, which is denoted by R squared, and its value ranges between 0 and 1. So R squared is simply, it indicates the percentage of variation in dependent variable that the independent variable explains. So we also have adjusted R square, which we use for multiple linear regression. So this one is preferred over R square because it considers all the X variables in the regression analysis. So this will give us a better observation, better output of our observation. So this is preferred one. And we have this estimated regression model, which we described earlier. This is the equation that we use to describe the relationship between independent and dependent variable. Also, we have dummy variable. Normally, we use numeric data for the regression, but in case we have categorical data like gender, marital status, or eye color, we have to convert this categorical variable into dummy variable, and then we have to use it in the analysis. So for example, if we have gender as male and female, we either use male as 1 or 0 or female as 1 or 0. So we can use it anyway. And if we have 3 categories like male, female, and others, we have to make a baseline for one variable. Either we make male as a baseline or female as a baseline, and other 2 variables we use as different number. For example, if we take male as a baseline and take it at 0, we make female and others as 1 and run the analysis. So these are the terms that we use in regression analysis. And for the interpretation of the result, we check the significance of the overall model. We use R square for predicting the value of the model. That is better the R square, larger the R square, better will be the accuracy of our observation. And we also check for the significance of independent variable. And also, if we have less significant independent variable, we remove it from the test and rerun the analysis and then compute the value of y. So I'd like to ask Eddie to have further presentation now. Thank you.
All right, thank you, Ravina, for that candid explanation and overview of regression. So I would like to wave off my screen and show you how we are going to run a test on SPSS. So I'll stop sharing right now. All right, so this is what SPSS looks like. So as you can see, we have tabs at the top with some other options. tabulated options. So this is how we import data into, this is a screen that we use to import data into SPSS and then we run further tests on it. So I am going to take the data from our source and then put it and then import it into SPSS. So if you could please bear with me. I'm just gonna copy and paste this just to save time. Go here. Okay, so I'll paste it here. All right, so I think I have to make some changes here. So what I'm gonna do is I'm gonna replace and speed. Oops. Right. Oh. Okay. All right. So I'll just delete the first row. So over here, we have imported our data into SPSS. So as you can see, they are aligned by the independent variables and the dependent variable. So the dependent variable that we are going to use for the regression analysis is the sales price in USD. And so if we want to run a multiple linear regression model, we will go to the Analyze tab, and then we will hit regression. And then we will hit linear. And so our dependent variable is the price in US dollars. So we can either drag this to this space right here. Or we can just hit this button. Or it says this is a string. Okay, let me just go here. This is supposed to be, so there are instances where usually the variables are represented as strings. So if you want to convert it into a numerical variable, you go to the variable view, and then you hit the type, and then change it to a unit of measurement. So once you hit that, you hit OK, and then you go here, and then I think that should work. So we'll go to Analyze, Regression, and Linear, and then we hit USD, and now it works. So in the earlier parts of the presentation, I hinted that it's important to represent your variables by unit of measurement. Otherwise, the regression model will not be able to detect what unit of measurement we're using. So we are going to use the first 5 variables as our independent variables and hit this button right here. It still says that string variables are not allowed in the list. So we'll have to go back and change them to numerical variables. So we'll go here and hit numeric, and it will change to numeric. The same for top speed. Same for range. The same for the efficiency. For fast charge. And now we should be ready to go. So we'll hit analyze, regression, linear regression. And then our price in US dollars is a dependent variable, and acceleration through fast charge is our independent variables. So when we go to statistics, we can select which indicators we want to show in our regression output. So we want to know the estimates, because the estimates will allow us to make some predictions in the latter part of the regression analysis. We can also include descriptive statistics, which will show our mean and our standard deviation of the variables that we are using in the analysis. So we hit continue. And the plot is used to represent your residuals. So if you wanted to fit your line, your regression line, you can just put the residuals in the Y and then put your predictive values in the X. And then that way you can be able to fit the line when you represent the output. So you hit continue. And then I'm just gonna hit paste. So once you hit paste here, it's gonna generate a code for you to run the regression analysis. Usually you can also hit paste, but if you would like to tweak your code in the future, it's better you represent it through a code format. So that way you can come back and then tweak things as you see fit. So I'm going to run this code right here. I'll highlight everything and hit this play button. And then another screen pops up, and then you'll be able to see the regression output of the analysis. So the first table shows us descriptive statistics. So it shows your mean and your standard deviation for all the variables that are used in the analysis. So as you can see, the average selling price of the electric vehicles that we are using in this test is about $63,000. And the average acceleration in seconds is 7.4. The average top speed is 180 kilometers per hour. Our range is 338.79. Efficiency 189.17 watt hours per kilometer, and fast charge is 435 kilometers per hour. And over here, we can use this correlation table to measure multicollinearity. So usually when we run regression analysis, we want to make sure that our independent variables are not correlated amongst themselves. Otherwise, it will lead to some bias when we make predictions. So this correlation table is very important. So if you wanted to measure multicollinearity, it will be easier for you to do that using the correlation table. And then we have a model summary, which allows us to predict adjusted R squared. And then we have this ANOVA table. So the ANOVA table will tell us the overall significance of the model. And then we have our coefficients, which shows the coefficients for each of the betas that are used in the analysis. So, and the good thing about SPSS is that once you generate your outputs, you can save the file by hitting file here. You can save it as a PDF or a Word document, and you hit export. So you hit this drop down and you hit export. And then in this dialog box, it says you can save it as a Word document, but you can also save it as a PowerPoint, as a text, as a PDF. And then once you do that, you hit browse to select the location in which you want to save your document. and then you hit OK, and then it saves it. I'm not going to do this for this part of the presentation, but for future reference, if you'd like to save your outputs, you have to hit File, Export, and then select the type of document that you'd like to save it in. So I'm going to close out of here and then go back to our presentation. Okay, so all right. So I'm going to So these are snapshots or snippets of the results that were generated in SPSS from running the regression analysis. So on the top left, we have descriptive statistics that shows your mean and standard deviation of all the variables that were used. And then we have a model summary that will allow us to predict or describe what the adjusted R-square means. And then we have the ANOVA table, which shows us the significance of the overall model. And then we have the coefficients that we'll use to make some predictions, and also to predict the significance of the independent variables in the study. So Rabina earlier on provided a framework for interpreting our regression analysis. So we'll start by analyzing the significance of the overall model. So if the significance from the ANOVA table is less than the alpha of 5%, which is our common baseline, then the regression model will be considered good. If we look at the table, if we look at the ANOVA table, we see that the significant B is 0.01. So that is significantly less than our alpha of 0.05. Therefore, we can conclude that the model is valid. So once you analyze and assert the first part of the interpretation, then you move to the second part, where we have to predict the value of the model or the accuracy of the model. And we do that using adjusted R-squared, as Rabina stated in the earlier parts of the presentation. So from the model summary table, we can see that our adjusted R-squared is 0.696 or 69.6%. So what this means is that about 70% of the total variation in the sales price of the electric vehicles can be explained by the acceleration, the top speed, the range, efficiency, and fast charge. Usually 70% is a good number for adjusted R-squared because it tells you that your independent variables are perfectly correlated with your dependent variables. So this is a good number. Then the next step is to check the significance of each of the independent variables. So if the significance of the coefficients are less than the alpha of 5%, then they are good variables. So when we look back at our table here, we can see that the significant variables here are our top speed and the efficiency. This is because these two variables are less than 5% significance level, but the rest of the variables in the study are greater than 5%. If you look at acceleration, it's 16.3, which is greater than 5. Range is 14.6, which is greater than 5%. And then fast charge is 81.2%, which is greater than 5%. So the only valid indicators of valid independent variables in the research are the top speed and the efficiency. So next we compute the regression equation. So in earlier parts of the presentation, the Y will be our price USD, and we represent it using a hat because the hat tells us that we are about to estimate the value of the price in the regression equation. Then we have the intercept that's represented by beta node. And then we have beta 1, which is a slope of the first independent variable, which is acceleration. And then we have the slope of the second independent variable, which is top speed. And then we have the slope of the third variable multiplied by range, the slope of efficiency, and then slope of fast charge. And so when we look at that coefficient table again, we can see that the unstandardized B values are the estimated values of each of the independent variables. So we will substitute that for the betas in the regression equation. So we get negative 119,913 plus this whole thing. And this is very important because without having estimated values, we can make predictions. If we want to compute the estimated price of an electric vehicle, we can use this formula to calculate it. We need estimated values for the betas to make that calculation. And in latter parts of the presentation, I will give you an example of how we can make such predictions using two scenarios. And the next step is to exclude all the insignificant variables and write a new regression equation. So the only significant independent variables in the equation were top speed and efficiency. So we'll write a new equation saying that the price in USD hat is equal to beta node plus beta 1 times top speed plus beta 2 times efficiency. And so we rerun the analysis and then we got a new output. So when we look at the output on the right, we can see that the adjusted R squared is similar to the one in the previous model that we run. And the significance is still the same. So the significance from the ANOVA table or the model is less than 5%. And then we get a newly estimated equation where we have the price USD in hats represented by the unstandardized betas. And as you can see from the right part of the coefficients table, all of them are significant at 5% significance level because they are all less than alpha of 5%. So let's use two scenarios to make predictions or to estimate the price of a vehicle. So in scenario one, we said that if an electric vehicle has a top speed of 225 kilometers per hour and an efficiency of 193 watt hours per kilometer, what is the estimated price? So our intercept is going to be a constant, so we don't have an X value for that. And our top speed, the coefficient for top speed will be 697.52 multiplied by 225, and then we get this value. And then our efficiency, which is 152, the coefficient will be multiplied by 193 watt hours per kilometer. And then when we make those computations, we get a total of $95,630. So that's our estimated price when we input these variables into our regression equation. And then we are using a different scenario where another vehicle has a top speed of 180 kilometers per hour and an efficiency of 120 watt hours per kilometer. So when we make these computations and we replace the S values by the numbers that are in the scenario, we get 53,134, which is way cheaper than the first scenario. So we can see that as X changes, the Y variable also changes. And the good thing about regression is that the relationship is linear, right? So a change in the X variable will lead to a proportional or direct change in the Y variable. So as you can see here, when we reduce the top speed and efficiency to 180 and 120, we got a lower sales price for the electric vehicles. And in scenario one, when we had a higher top speed and a higher efficiency, it led to a higher price of 95,000 or almost 96,000 US dollars. So thank you very much for attending this session. And if you have any questions, please feel free. We'll be willing to answer them. Thank you.
Thank you very much. That was the end of our 3 series workshop. I hope you learned something, out of these 3 workshops, and we highly recommend that you come and see us if you have any research that you might need statistical analysis to be run on.